Okay, in this video I'm going to cover modeling an unconditional three-level multi-level model um, where we have repeated measurements at level 1. This demonstration comes from chapter 6 of Heck et al.'s book Multi-Level and Longitudinal Modeling with IBM SPSS. Chapter 6 basically is called Applications of Mixed Models for Longitudinal Data. So in the presentations within this chapter, the authors uh, model variation in graduation proportions from different institutions. So, and those institutions are nested within different states. So grad proportion is a level 1 repeated measurement. It's our outcome variable. And what we have are measurements for each institution over a span of 11 years. So you can see that we have this is institution 1 in our data set, we have a variable called time, which is coded 0 to 10, which spans actually an 11-year period. And then we have grad proportion for that institution over the 11-year period. We have institution 2 over its 11-year period as well. So there's time starting at 0 going to 10 over the 11-year period and so forth. These institutions are also nested within different states. Now, really quickly, time you'll notice is coded 0 to 10 instead of 1 to 10, and that's by virtue of coding it in this kind of way. When we include time as a predictor in the model, then it helps us to better interpret or make some sense out of the intercept. In that case, if we just included time as a predictor, the intercept for our model would be the essentially the average, time 1 measurement or average grad proportion at time 1 across states. So we're not going to include time in this particular demonstration. Like I said, we're going to utilize or carry out an unconditional model where we're just going to break down the proportion and variation in grad proportion, or break down the variation in grad proportion at the different levels. So so also note that we have a variable in here called RID, and basically it's just taking this ID variable and recoding it so that it captures a case or institution number within each state. So these numbers actually will repeat as we move from state to state. So you can see that we have, these numbers right here are all associated with state 1. So we'll see right here, there's 15 institutions nested within state 1. Each of these are the unique identifiers associated with the state. Then we kind of start over here, and you can see we've institution 1, 2, and so forth within state 2. So that's how this is broken out, and the authors kind of utilize this variable. They suggest it helps to reduce computation time, and probably also helps with just estimation in general, or getting the model to run. So at any rate, we're going to go to Analyze, Mixed Models, Linear, and what we'll do is we'll move RID over to the subjects box, state ID over. We need a variable that reflects, that captures a timing or repeated component, so we're going to move time over to the repeated box. When we do that, this box highlights down here, and this just basically addresses the question of how we want to treat the variances and covariances of the errors associated with the repeated measurements. Diagonal matrix basically assumes or treats the errors as being heterogeneous. So we essentially estimate the variance of the errors at each time point uniquely. So now the covariances are going to be modeled on the off diagonal, and the covariances are actually going to be 0. So in this case, we would have essentially, given that we have 11 measurement occasions, we'll have 11 error variances at level 1. So that's a lot of parameters that can be estimated. Another option is to select scaled identity, in which case we would assume a common error structure across a repeated measurement. So instead of having 11 error variances being estimated, we would have 1. Also with this, we would have a 0 on the off diagonal. In short, we would still assume no correlation or covariance between the errors between repeated measurements. We also have an AR1 autoregressive 1 process. In this case, right here, we assume essentially equal error variances across the repeated measurements, but we would also assume correlated errors between adjacent time points. If we select an AR1 heterogeneous process, then we're assuming still the AR1 process, but also assuming that the error variances would be heterogeneous. So in the case of the AR1 process, we're actually estimating 2 parameters, an autoregressive parameter and the error parameter, the variance of the errors at level 1. An AR1 heterogeneous process means that we're estimating the autoregressive component as well as essentially 11 variances. So you can see that the covariance type that you select has an impact on the number of parameters that are being estimated. If we selected unstructured, that would mean that we would have essentially 11 error variances that are being estimated, as well as all covariances on the off diagonals. So you can see that this would yield really the largest number of parameters being estimated. So just keep in mind that we're trying to find a balance between the appropriate covariance type at level 1 and number of parameters that are being estimated. The more parameters that you estimate, the more likely you will have model convergence problems. So you just have to kind of keep that in mind when you are making your decisions, whether it be in a 3-level situation like this or a 2-level situation like we saw in chapter 5 of the book on repeated measures. So we're going to stick with the example provided in the text, going with an AR1 process. We'll click on continue and we'll move grad proportion over to the dependent variable box. Fix we're going to leave alone. All we're going to be doing is estimating the intercept, the grand mean, which would be the average graduation proportion across states, and essentially that's across the institutions and across the years. So it's a grand mean in terms of graduation proportion. The random component, we're going to be estimating variation across states and then also across institutions in terms of the intercepts here. So I'm going to click on include intercept, move state ID over to the combinations box. We again come up with the covariance type. The default is variance components, but stay true with the presentation in the book. We'll go with a scaled identity, although it's not going to make any practical difference. There's only one variance that's being estimated, or one parameter is being estimated at level 3, and that is the variance of the intercepts across the states. So it's not really going to make that much of a difference, but we'll click on next, and then for a random effect 2 of 2, we'll click on include intercept. We'll also still select the scaled identity, and we'll move the RID variable and state ID variables over. Click on continue. Under estimation, we'll stick with restricted maximum likelihood, and under statistics, we'll go with parameter estimates, test of covariance parameters, and covariances of random effects. Click on continue and on OK. And so now you can see that we have right here, we've got our model dimension covariance structures that's been laid out. You'll see that we have 2 parameters estimated at level 1, which includes the error, essentially one error variance, and the autoregressive component. So that's why we have the 2 parameters being estimated here. When we scroll down, we have various fit indices. Just keep in mind that these are a little bit more tricky to interpret in the context of REML estimation. So just kind of keep that in mind. When we scroll down, you'll see estimates of fixed effects. So essentially what we have right here, this is the, I guess you could say, the grand mean of the graduation proportions. So this is essentially reflecting the proportion of the average proportion, or the proportion average across the states, which is around 43% of the students were graduating from their institutions. When we look down in terms of the covariance parameters, you'll see repeated measurements. We have the A1 diagonal. This is the variance estimate. The AR1 row, this is the autoregressive component. So, and you can see that this was, significant, as well as this right here. So clearly, we have variation at level 1 that can be explained potentially. We also have variation in the intercepts across states, so that's the variance estimate, and it's statistically significant. So theoretically, we might add in state-level variables to predict variation in graduation proportion across states. And then we see the variance associated with the at the level 2 institution level. The intercepts was also significant as well. So we might add in level 2 predictors or institution level predictors to model variation in intercepts at that level. So if we want to compute the ICC, or the interclass correlations for our model, what we can do is, I've already kind of worked it out in Excel. What I've done is I've basically input the these estimates. So the level 1 estimate is 0.004, so I've basically typed that in here. Level 2 estimate is this one right here that's got the RID, which is 0.016397. So I just basically typed in 0.016, and then 0.003 for the level 3, and so that's it right here. So the ICC was just computed by taking a ratio of each of these numbers and dividing it by the sum of these variances, and so that gets us a proportion of variation accounted for at each level, or proportion of variation at each level. So you can see that the between state variation is roughly 13%. The between institution variation is roughly almost 70%, and then the variation at level 1 is about 18%. So that's essentially how you can look at this. So all I've done is just taken each, the H column and divide it by, you can see right here, I've just taken H column, H5, H6, H7, and dividing it by the sum of the cells for H5 through H7. So that's all that was. One other thing to note is that they discussed in their presentation for this model is they kind of ran several different models and made some model comparisons using the I believe it was the Keiki's. No, actually they just utilized the -2 log likelihood, or the -2 restricted log likelihoods, and so just kind of really quickly. This is it right here. This is what they were referring to, and so just kind of as a point of comparison, just to kind of show you, the basic idea is that the information, you can see, is displayed in smaller is better form, and one of the unique things about this model is that we ended up with negative values on these indices, and so you have to kind of keep it in terms of the negative doesn't really the smaller is better issue is a little tricky, because technically the best structure actually was that they came up with was an autoregressive heterogeneous structure with a -2 log likelihood of -18,988. So I'll just kind of show you that one right here. If we run this using heterogeneous and clicking on continue and on OK, it takes a second to run. And remember, the reason why is because we are having to estimate all of these variances right here. Previously, we had only estimated the diagonal, AR1 diagonal, that one common variance, and assumed autoregressive structure. In this case, we had to estimate now all of these variances associated with the time points and the autoregressive component. So you can see that it just kind of increased our time to the final iteration, or to the final estimation. But you'll notice that in this case right here, we've got a negative 18,988, and basically the negative sign, according to these authors, it does matter. And so we prefer the smallest value of fit indices, and they basically said that in the order basically the heterogeneous model fit better than the just the standard autoregression 1 model. So the long and short of it, that's what they decided on. Just to kind of give you another demonstration using a different strategy, we'll use the diagonal matrix. In this case, we'll be estimating the variances for each of the time points. Oops, hello. And so in this particular case right here, you can see that we have the variances. There's no autoregressive component, but we are still estimating error variances. And so when we scroll up, you can see right here it's a negative 17,672. So this is worse fitting than our previous 2 models. So that concludes this general overview, and I hope you find this helpful.